Tapas sir, yes sir.
Good
How are you,
afternoon.
sir?
I'm fine. How is Jyotirmoy?
Jyotirmoy is now ready to deliver his
Good
talk.
afternoon, sir. Yeah, so we were struggling to find speakers, so I volunteered.
No. We are also very eager to listen to you.
Thank you.
How are you, Sandeep?
Fine, sir. We'll just wait for 2-3 minutes more because our secretary, Sir Shantanu Bose, sir, will be joining after 10 minutes. I think he's driving or something. He just informed. He told me we need another 10-15 minutes to join.
Yes. We'll have to wait 10 minutes at least.
We'll try to start by 5 minutes past 4. Then eventually he'll join.
Yeah, okay. I think 14 people have joined so far.
Right, sir.
I have seen Dipta Datta.
Now people are joining. There are more than 70 apart from myself.
Susmita Ghosh.
So Jyotirmoy, your talk pulled me out of bed at 5 in the morning, 5:30.
Wow, sir. Thank you very much for tuning in.
I'm still trying to wake up.
Yeah, I wish I could send you a cup of coffee.
No, that's okay. I'll take a rain check next time I go to India.
Yeah. Thank you very much. It's really early for you.
Dhruva Babu is here, so I'm sending my pranam to Dhruva Babu.
How are you? How are you, Neptune?
Sir, bhalo achi, you are well. We saw your picture in Ghatshila outing. I wish I was there.
Yes, it was a nostalgic field trip. But
I'm sure you noticed something new.
Both of them, they have changed beyond recognition.
Sir, Gautam Mitra was here last week. Judy and Gautam Mitra.
Florida.
Yes. Okay. Well, usually he once a year he comes here to watch birds and stay at my place, and we have a good time together. Talk lots of geology all the time.
Okay.
So Jyotirmoy, I saw another Jyotirmoy Mallik in newspaper. I'm sure that was not you, right?
I mean, as a reporter, no, perhaps not.
No, that Jyotirmoy Mallik was a minister. Now I think he's in jail.
Oh, that is Jyotirpriyo Mallik, sir. We have a very, similarity in name.
Your cousin.
That is
actually, that Jyotirpriyo is from my school, actually.
It's not.
Okay. No, Balu Mallik is from Scottish school, sir, from my school. But anyway, I'll turn my mic off now. Shantanu.
Shantanu sir has joined. Dr. sir is already here. So, Jyotirmoy, if you are ready, and then
I'm
start
ready.
today's meeting, I think. So, good afternoon to all of you. I welcome you all to this online platform of Structural Geology and Tectonic Studies Group India, and we are really delighted to welcome Dr. Jyotirmoy Mallik of IISER Bhopal to deliver the monthly lecture of March 2024. Just to give you a brief idea about his career, Dr. Jyotirmoy Mallik is currently working as an associate professor in IISER Bhopal. Prior to joining academia, he has a vast experience in the petroleum industry, having served shale as a structural geologist for about 9 years. And later on, Dr. Mallik earned his Ph.D. degree in 2008 from IIT Bombay in association with University of Heidelberg under DAAD exchange program. And he is currently also heading the Department of Earth and Environmental Sciences at IISER Bhopal. So now I hand over the platform to Dr. Mallik and invite him to present this month's e-lecture on the topic potential of permanent sequestration of carbon dioxide in the Deccan Basalt of India. So over to you, sir.
Thank you very much, Shandip. For the sake of better internet connectivity, I will just switch off my camera so that the internet works better. And
yeah, no problem.
Yeah.
You also
I hope you all
go
can
to the full screen. Yeah.
Yeah, and I will do the full screen now. Is
Right,
it visible now?
Right. It is now visible clearly.
I'll just a moment. I think the arrow will work fine. Okay. So today I'm going to talk about the potential of permanent sequestration of CO2 in the Deccan Basalt of India. And I must say this is a very early phase of work. We just started working on this project just 1 year before. But I think there is a lot of work in this domain currently going on. And I thought it's a good idea to share some of our early learnings with the community and get some feedback. So I must thank my co-investigators, Dr. Nimisha Vedanti from CSIR NGRI and Dr. Ravi Sharma from IIT Roorkee. We are working very closely actually on this project. So the project is under an international consortium. We three, as I have just said, myself, Nimisha, and Ravi are Indian partners. However, this particular project, which we call as PUBUS stands for Permanent Sequestration of Gigatons of CO2 in Basalt. So we are looking at the North Atlantic margin as well as the Deccan Basalt. And there are 10 institutes working on the same project across the world, from Norway, from from the US, etc. And this is under the ACT call of DST. ACT stands for Accelerating CCS Technologies. So thank you to DST as well for sponsoring this mega project. So why we are talking about permanent sequestration in basalt? So as you know, our Prime Minister has given a mandate that India should reach net zero by 2070. And IPCC did a study where they have looked into different options, and they have found that if we wish to achieve net zero by whatever timeline it is, and if we do it without any CCS venture or carbon capture and utilization and storage venture, essentially your budget will be 140 times more expensive. So this is part of the total scenario with which we are trying to reduce net zero. So those who are pretty new for what is carbon capture and storage is, So essentially, the idea is you capture carbon dioxide from source, and then you either mix it with water, or you essentially compress it to supercritical fluid and then push it back through wells into a geological formation. So that is what is all about carbon capture and storage. U stands for utilization. We are not working on utilization. Utilization essentially means that converting that captured CO2 into some sort of product that can be used for our livelihood. However, we are not working on utilization. We are mostly working on the storage problem as geologists. So, if we want to have a successful venture of CCS in India, that should include identification of storage site where we wish to do that storage, improvement and cost reduction of capture and monitoring technologies, and development of transport infrastructure, because always your source and sink might not be at the same place. And of course, there is a great work that is lying ahead of us is in around policy and regulatory framework that includes implementation of the carbon credit system as well. Now, in general, there are few recognized or laboratory studied sites, or in a sense reservoir that people think, or sink people think could be potential for CO2 storage. One is basalt, on which we are working. It could be depleted oil and gas reservoir because it had stored oil and gas before. So the idea is it could also store the carbon dioxide, saline aquifers, and unminable coal seams. Our particular interest is in CBM, is in basalt. Now, this is a map that was published by Vishal et al. In 2021, which actually who did a, very preliminary calculation of the storage potential of different geological units that we find in India. And I want you to look at the number that is associated with the Deccan Basalt, that is around 94 to 305 gigatons of storage potential that they have proposed. However, this is based on extremely crude calculation, and there is a lot of improvement on what that essential number is. But even if we just take it at the face value, what it shows you that it has a lot of potential in terms of CO2 sequestration. The storage is actually huge in case of Deccan. So, why we are thinking of the relevance of basalt as a CO2 sink? In case of Deccan, it has a very vast aerial extent, as we all know. Of course, Rajmahal Trap is there too, but we are not looking into Rajmahal Trap as yet. It has a very large storage capacity, as I have just said. They have Vishal et al. Proposed a number of around 94 to 305 gigaton. And there are presence of abundant vesicles, joints, fractures that would essentially enhance the porosity and permeability of the Deccan basalt, because massive basalt, if they are not, they will not be porous and permeable. So it will be very difficult to actually pass your fluid through them. So as a result, you require basalt which has some porosity and permeability, and it has been established that Deccan basalt is at many places. It's with a lot of vesicles, joints, and fractures, which could enhance the porosity and permeability. The most important thing is that why people are interested in basalt is that it has the least risk of leakage. So in all other geological storage options, what you are essentially doing, you are leaving the CO2 in the gaseous or supercritical form in the subsurface. So they are not essentially reacting with your rock. In case of basalt, however, the CO2 and water mix, which will form carbonic acid, that would react to almost all the mafic minerals as well as plagioclase feldspar, and then create siderite, calcite, magnesite, as well as clay minerals. So what that essentially means that you could eliminate the CO2 from its gaseous form altogether. You are actually making some chemical changes and you are forming rocks. So the CO2 is essentially completely eliminated from the system. As a result, the option of basalt is being looked at with a lot of interest nowadays, not only India but across the globe. So these are these are some of the flood basalts which people have identified, which could be potential sinks for CO2 sequestration. Within them, you can see here the Deccan Basalt, its offshore and onshore part. However, right now we are only looking at the onshore part. Currently, there are two projects that are actively going on where CO2 sequestration is happening in basalt. The one which is very much talked about is called the Curve Fix project, that is in the Iceland, and that is doing very well. It has almost like a 400 gigaton capacity, and it's one of the success projects that had given people a lot of hope that CO2 sequestration in basalt is perhaps a viable idea. So a lot of CO2 is being sequestrated as we speak in the Curve-Fix project. However, there is another project which is in the Columbia River Basin, which is called the Wallula, where of course it has a lower capacity, but it's but one thing that is happening, that it is actually performing less than what people have expected. So we have one scenario where it is performing more than what is expected, and we have another scenario in Columbia River Basalt where it is actually not performing as good as people anticipated. So we don't know how it will be for Deccan Basalt. Time will tell. But this is the scenario right now worldwide. So what essentially you do? So you have you collect your CO2 from a source, and then you separate all the other NOxes and SOxes from your CO2, make it pure CO2, mix it up with water, and then essentially pump it back into the geological formation. In this particular case, this is basalt, right? And this paper by Millet et al. Actually shows you different volcanic fascies that you can associate with a large igneous province, like for example, sub-basalt volcanic seals, intra-basalt volcanic reservoirs, inter-basalt volcanic seals, etc., ashes as well, for example, and also the intertrapians, which all could be potential storage volumes. So in the project Parbas, what we are willing to do after 3 years is to produce a multi-scale geological model calibrated with experimental data. So we will develop a comprehensive description of the basalt by characterizing samples from cores from drilled boreholes. So we have around good number of 20-25 boreholes to look at, both from Koina and Kilari region, as well as samples collected from fieldwork, and then analyze the data and kind of come up, and also analyze some of the seismic data which is available, and come up with a reservoir model which could be used for several purposes. For example, designing geophysical monitoring, doing your reservoir characterization. You need to do a lot of geochemistry, of course, because it's a geochemical sequestration, as well as the cap rock integrity, etc., etc. So that is the aim of our project. So what I'm going to talk about today, I've just gave you an introduction. I'm going to take you through some of the field. You all have seen Deccan Basalt from many times, I'm sure, but I'm going to take you through the Deccan Basalt from the CCS perspective, how we look at Deccan Basalt in the field from CCS perspective. Some of the early lab studies and results that we have got, and some major takeaways. So that is what we are going to talk. So, Deccan is a large province, right? So we cannot concentrate everywhere. So we initially have chosen the Deccan Central Mainland, as we call it, Deccan Mainland. Of course, there is Saurashtra Plateau, Malwa Plateau, Mandla Plateau, etc., which is still left to be actually studied. But we have started with Deccan Mainland because that is the most studied, and we have the maximum number of literature present in that area. Okay. The other important reason why we have chosen Deccan Mainland, because in Kaufik's project, what they have also shown is compound power-wave lava flows are perhaps the best candidate for CO2 sequestration. And we see an abundance of strongly compound power-wave lava flows in the Deccan Mainland. And of course, this is the Deccan stratigraphy. For Indian audience, I do not need to repeat about how the stratigraphy is. Especially in Deccan Mainland, we generally find formations from Bushe, Poladpur, Ambenalli, and Mahabaleshwar. There are exposures of older formations as well. However, currently we are focusing on Bushe, Poladpur, Ambenalli, and Mahabaleshwar to some extent. Because another thing which has been seen also, that fresher the basalt, you get a better sequestration rate as well. So this is the thickness variation of Deccan, and this is from magnetotelluric study. And what we generally observe, there is a general thickening from east to west. Eastern part can be pretty thin, a few hundred meters, to a few kilometers it can be in the western part. So it is important to know if you start to design your CCS project, how the thickness is actually varying in your study area. You need a considerable amount of thickness to make it viable, right? You cannot just do it at a very shallow depth. So these are some of the photographs of vesicular basalt that you find in Deccan. And you can see, for example, this picture, that a part of the basalt where the vesicles are not much connected. So although it will have some porosity if you calculate, but the permeability will not be very strong. However, if you are moving few meters away, the vesicles could be extremely connected. It's not only about finding the vesicles have to be open as well. In many cases, we do find that the vesicles are actually filled. It could be filled with calcite as well as quartz. The calcite, filling of calcite, however, kind of hints to the process of natural sequestration and gives you some sort of hope that naturally also CO2 is being sequestrated in Deccan Basalt. However, the unfilled vesicles are the ones that are of your interest. Here, for example, in this picture, you can see in the third picture, the vesicles are completely unfilled. In a compound lava flow, what you generally observe that the bottommost part is actually vesicular. The topmost part could also be vesicular. In between, there is a massive core, which is non-porous, non-permeable. However, if this core is essentially extremely fractured, in that case, you might connect the upper vesicular zone with the lower vesicular zone. Sometimes the vesicles look like pipes. It all depends on how the gas essentially escaped from the lava. Okay. So the moral of the story is there is a high variety. I mean, the variability is pretty vast in terms of the presence of vesicular basalt in Deccan. So one of our objective was how to essentially calculate porosity in these vesicular basalt. Now, one of the things that I just tried to emphasize that in many cases, the vesicles might not be connected to each other. In that case, the traditional processes by which you calculate porosity might not work because, say, for example, you have a sandstone core and you are trying to calculate porosity. The fundamental is that the porous spaces need to be sufficiently connected. Otherwise, you do not really get a very good result of porosity that it will not truly represent the porosity that it has. And what we have also seen from earlier studies that you will require at least 20% of porosity to get them connected. So for that, what we have started doing is also trying to calculate porosity from high resolution images. So we are looking at CT scan images of the vesicular basalt and trying to calculate from different scan lines the amount of porosity and then average them out. So we are looking at the CT scan images. We are looking at stereo zoom microscopes. We are also looking at ACM images. We are also looking at, simple images taken by a camera and trying to compare what sort of porosity we get in different resolution. If I look at the ACM image, another important thing, this is a close look, is a very close look of a basalt, and you will observe that the outer rim of the vesicle is kind of fractured. So another thing what we have also observed that if you put these basalts under thermal stress, these micro cracks actually connect with each other and they can actually enhance the permeability. So what has been seen that there might be cases where the initial porosity and permeability of the basalt is low. However, once you put the water and CO2 mixture into it and there is some sort of thermal stress, and that can enhance the porosity and permeability. What happens, these micro cracks actually join together to form some permeability pathways. So currently we are looking at these different resolution images and trying to calculate porosity. Of course, we are doing the traditional way of calculating porosity and trying to make a comparison of which particular process is actually giving us better result. So these are some of the very early results. So as we have said, we have just analyzed few samples and the results are encouraging. I'm not going to comment on the results more right now. The results are encouraging, and we might be able to propose an alternate way of calculating the porosity of these vesicular basalts from an image-based technique. Now, the other kind of basalt that we are also interested in is the fractured basalt. Now, this fractured basalt generally do not have a lot of porosity. If the massive basalt gets fractured, the matrix porosity is essentially very low. However, there is fracture porosity and there is fracture permeability. Say, for example, if you look at dikes and some of the flows which are extremely fractured, here also the traditional way of calculating permeability fails because of the sample size. Because what you will do, you will take up a core and that core will not contain enough number of fractures which can be used for a successful calculation of permeability. So for that, what we are also doing is called creating discrete fracture network models. So we have sampled hundreds of dikes and fractured basalts across Deccan, and then in the central mainland, of course. And then we are trying to create fracture models out of them, which we call as discrete fracture network model. And that is being done in a software called Move. And this is essentially digitizing your fracture pattern, and then you are assigning aperture values to them. And the aperture essentially decreases with depth because of the effective stress. The aperture essentially decreases, right? So what that will give you a description of permeability from the surface to the depth at which you are interested to carry out your CO2 sequestration. So permeability characterization by discrete fracture network modeling is another area in which we are looking at very closely. So this is how a permeability model essentially looks like, and you can see the surface permeability can run all the way up to 3 to 5 Darcy, which is a very good number. So really, really good number. And then, of course, if you apply fracture compressibility to the system, you should be able to also calculate at a particular depth what would be the permeability. And of course, these permeabilities are tensors, right? So they are they're different in the X, Y, and Z direction, and depends on how your fracture is actually distributed, how your fracture network is actually distributed. So what we are also doing, we think that the dikes have a very good potential in providing very nice permeability pathways for CO2 sequestration. So we are trying to calculate what sort of volume of CO2 one dike can actually sequester. And you will be, I don't know if you are already familiar with that, these dikes can be kilometers long, 11, 12, 30, even 30, 50, 100 kilometer long dikes are there. They're of course not very thick, but if there is a long dike, the idea is, of course, the dike will be also extending pretty deep. So, however, because of the presence of cooling joints, you are kind of have a guarantee that these dikes will be fractured, right? And we are currently looking at creating reservoir models from these dikes and trying to understand the permeability distribution as well as the volume of CO2 that these dikes can actually hold. And these are some of the numbers. And in the high case, I mean, in a very optimistic case, one particular dike, which is around 3 kilometers long, can sequester up to 0.4 megaton of CO2. And India and Deccan Basalt, as you know, it has thousands of dikes distributed along 3 major dike swarms. So that is another piece of work that we are doing. This is the distribution of dikes. You can see the central mainland is kind of infested with dikes, if you like. So this is the West Coast dike swarm. This is the West Coast dike swarm. The Narmada Satpura Tapi dike swarm along the Narmada Tapi Narmada Son lineament. The Pune Nasik dike swarm. So currently we are focusing on the Pune Nasik dike swarm because this is pretty extensive, and we think that if we just target the dikes, there is a possibility that it can also sequester gigatons of CO2, where the permeability will be pretty much guaranteed. Okay, so the major takeaway points. So in Deccan mainland, we find massive basalt, fractured basalt, vesicular basalt. The inhomogeneity in the reservoir architecture is really appreciable, and which would certainly affect the porosity, permeability, as well as ECO2. Now, ECO2 refers to the efficiency of CO2 being converted into minerals, and that is something which is not established in case of Deccan Basalt at all. And if I refer to a picture here, you can see here, this is the the general values of ECO2 that people have given, not from Deccan Basalt, from elsewhere in basalt, that ranges between 18.8 to 48.7. Now, that number, that uncertainty must be reduced, because that kind of gives you a very wide range of CO2 that can be sequestrated. So there is some chemical kinetics related work is also going on in our lab, where we are trying to establish from experiments as well as from theoretical modeling that what sort of ECO2 is applicable for different types of Deccan basalt, especially in central mainland, especially if we are concentrating on Polatpur, Bushe, as well as Mahabaleshwar formation, Amenali and Mahabaleshwar. So the work right now is to reduce uncertainty, and one should be able to reduce uncertainty once they can appreciate the amount of inhomogeneity that is present in Deccan basalt. And then, of course, more and more studies are being done. So the vesicular basalt show a variation of porosity, which is from very low to 2.3 to 15%. Image-based technique could be a good alternative to the conventional method. The fractured basalts, especially the dikes, show very high permeability in the range of 6 to 8 Darcy. The permeability will decrease with depth depending on the fracture compressibility, of course. And the Deccan dike swarms could be the potential sites for CO2 storage. So with that, I stop my quick presentation, and then I would love to answer any question that you might have.
Thank you, Jyotirmoy. Now the platform is open for any kind of queries. So I request the members of this group to come up with your queries. Neptune sir, please go ahead, sir.
Okay. Jyotirmoy, wonderful talk and very interesting. And of course, we have such a huge resource for absorbing carbon dioxide. That's amazing. Well, earlier in your talk, you mentioned that it's been very successful in Iceland, right? And
Iceland,
have they looked into the reasons why it's very successful? It's because of higher temperature, or because of active lift going on, or what?
So there are few things to it. So the basalts that you find in Iceland are very fresh. So the ECO2 is very high. There is also a very high geothermal gradient, because I mean, what people have shown, if I can raise the temperature to 150 degrees centigrade, then basalt converts into carbonates in days, actually, not even months, in days. So the reaction rate is very high. So if you could sequester at 800 meters or so in Iceland, you are actually flying. Also, there is good amount of porosity and permeability in Icelandic basalt. So there are many things happening very nicely for Icelandic basalts. So, but in my opinion, it's a very special case. It's not going to happen everywhere, because Deccan doesn't have that geothermal gradient.
No, but in the regions where you have hot springs, do you think that those will be more suitable for sequestration within Deccan basalt?
How the important thing that we have to understand here, that how extensive is the effect. Whether the effect is pretty large, the aerial extent of that hot spring is very large or not. If it is not, then you are thinking about storing gigatons of CO2, not just setting up a pilot plant. So that is something we need to understand.
Okay, thank you.
Yeah.
Jyotirmoy, a question from a layman who doesn't understand much about these things. Unless the CO2 is fixed through some reaction, what is the guarantee that eventually with time, it will again escape into the atmosphere?
Sir, it's being fixed with reactions only, right? So if I go back to the
yes, I mean,
slide.
how much of the CO2 is fixed by reaction?
How much of the CO2?
What proportion of the stored amount is fixed by reaction?
Sir, that is, I mean, what we have are the results from laboratory studies and one live example from Carfix. In Carfix, they say it's almost 95% of the CO2 is being converted into minerals actually. And in laboratory studies, if you can increase the temperatures, I mean, right amount of temperature, almost 100% goes away. But what it would be in the field, that is difficult to say, because most of the laboratory experiments are done where the basalt is crushed, so you have a very high surface area. um, However, it will not be crushed in the subsurface, right? So it is the porous space, it is the permeable space through which it will find its surface area to react on. So there is another risk to it, that is, if I go back to my first slide, you can see here that this vesicle is kind of filled by calcite, right? Now, if there is a high amount of volume increase because of this reaction, the porosity will be clogged, so there will be no more CO2 which can infiltrate through this porous permeable network. And then, as you rightly pointed out, the amount of carbon dioxide which we push, 100% will not be sequestrated. But in Carfix, they have a very high conversion rate, and in the laboratory experiment, you can almost do 100% of the CO2 converted into other minerals.
What is the range of temperature in your laboratory tests?
Yeah, it's around, sir. So the most around 150 degrees centigrade is the temperature where you see a very good result. Around 120 degrees centigrade, the reaction rate is slow. However, it takes around 3 to 6 months for things to be converted. But if you can increase up to 150 degrees centigrade, it's matter of days.
Jyotirmoy, sir, if you are over, then I have a related question to clarify. What is the depth then you are targeting? 5 kilometer above?
No, we don't know the depth yet. So it's very early to say what is it going to be for Deccan Basalt. In case of Iceland, it's around 800 meter to 1 kilometer. But they have a very high, steep geothermal gradient.
True. So, for example, you have said that there are two layers in our Deccan Basalt where you have large amount of vesicles, right? One in the upper, and there is in the middle there is a less amount of vesicles, and below that again a vesicular structure.
No, that is for a single flow. So those flows are present everywhere. However, the upper basalts are targeted because they are fresh. Fresh basalts react better with the CO2.
So what is the depth? I mean the thickness. According to the thickness, what is the maximum depth that you have?
Thickness essentially varies. So it depends where you want to do your sequestration. In central mainland, it can be say for example around 100 meters or so.
So in that case, you will not be achieve the temperature that you are getting in your experimental studies.
No, 100 meters thickness. Depth it can go all the way up to 1.5 kilometers. So in that case, you have to essentially increase the temperature of your fluid itself and then push it down.
Okay. So another thing that Jyotirmoy, that I want to know, so what is the rate of flow that you are giving, that mixing of the water with the carbon, that is when the carbonic acid that you are pushing there?
Yeah.
There should be some rate, right?
Yeah.
what is the relationship between that? If you do it in a very faster rate, will it really absorb there?
No, that's a very good question, and I will be very honest with you. I think we don't have an answer yet. In case of curve fix, I think so. Since 2014, they have actually sequestrated around 85,000 tons of CO2, right? So this is 20. Matlab 10 years may 85,000 ton. So you can calculate actually. So around 8,500 tons per year.
Okay.
But that's minuscule compared to the gigatons that you guys are planning.
Oh yeah. So no, it is not going to happen every day. I mean, it is not going to. It's a long-term project, right? I mean, it's just not. I mean, it's not going to just. You are not sequestrating it in one day. It's like a well in the subsurface produces for 15-20 years, right?
No, but at this rate, it will take 1 million years to get a gigaton.
Yeah.
You have to drill many wells. Actually, you have to drill many wells. So Carfix is a demonstration project. Carfix is a demonstration project. Carfix is not a commercial project. They have not gone commercial as yet. So gigatons means that is the total capacity of Deccan Basalt. That now how much you will be able to sequestrate at what rate? These are two preliminary questions. I mean, too early to actually answer. Yeah.
Okay. Another thing, Jyotirmoy, just to know,
yeah.
How do you estimate the porosity and permeability at depth? Because then you'll have to drill up to the level.
Yeah. You have to drill boreholes first. You have to take out cores and then get an idea, and then compare with your outcrops, because drilling
but how do you
wells are very expensive.
How do you guarantee that all the ports are connected?
No, there is no guarantee. There is of course a risk, but then you do some sort of phases mapping. Okay. You create reservoir model. You have like a low case, high case, and that's how the business goes for oil and gas. You have few wells based on which you prepare your model.
But another thing is that then can it be possible to make hydrofracturing on the basalt and then increase the permeability?
Well, so hydrofracturing is a very controversial topic, because hydrofracturing is supposed to be environmentally bad, and here you are trying to do something which is environmentally good. So so philosophically, perhaps hydrofracturing is not the optimal solution for CO2 sequestration.
But for oil companies, they do, right?
What is that?
Hydrofracturing is a very common practice in oil.
Yeah, absolutely. It happens everywhere. But as I said, this is an environmentally positive. Now, there are also a lot of people who speak against hydrofracturing, right? So, hydrofracturing is not an option what people look at in CCS very positively.
Okay. Yeah.
But Jyotirmoy, hydrofracturing is bad because you use lots of chemicals, you use up lots of water, and you might pollute the aquifer. But here you are using totally different things. I mean, you are going much deeper, possibly not polluting any aquifer, and possibly you would not be using those chemicals to free oil. You would not be using detergents.
No, you will. There is also a risk of contaminating aquifer. For example, all the fractured basalt of Deccan, they are very good aquifers. These dikes are actually recharge pathways for all the aquifers. So that is a risk what people have to actually account for before any successful CO2 sequestration study.
Jyotirmoy, I have a different question. Actually, it's a very good presentation, and if someone thinks of initiating a similar work in other volcanic provinces, especially in the tertiary fault thrust belt like Arunachal Himalaya, then what could be the preliminary considerations? For example, the extent to which the basalts are exposed, as well as the vesicles, as well as fractured part. What could be the preliminary considerations?
So first thing, of course, you need to look at the extent, the thickness, And then you have to know about its porosity, permeability in terms of vesicles and fractures. Then your reaction rate. That these are very few basic steps before any project can actually start.
Before embarking any project.
Yeah.
Okay. Thank you.
But this is highly encouraged now. I mean, there are many, for example, DST, SERB. I mean, if you wish to initiate such studies, and I think there are many studies which are being initiated. I know at least for basalt, there are 10 different groups which have started on different aspects of Deccan and have started working. So this is for some time. This is going to be here.
Yes.
Yeah.
Jyotirmoy, you have a question in the chat box.
Okay,
I think Shayan Maiti is there. He's just look at it.
Are there any specific criteria choosing the site of the well for pumping fluid? Okay.
And there is another one from Manav.
Yeah. So yes, of course there is. I mean, the specific criteria is it should have a good reaction rate. And the other very important thing is the carbon dioxide should not leak out. So you have to prove that in foreseeable future, not foreseeable, in geological future, you have to prove that for next 10,000 years, the CO2 is going to be within the rock. It's not going to come out. So this is one of the most important choosing criteria, that the CO2 has to be underground. It cannot leak out back to the atmosphere. And of course, it has to have enough storage potential as well. Yeah, Manav, for CCS industry, CO2 fracturing is an alternate method of hydraulic fracturing. It's going through pilot phase. Yeah, that is true.
Oh, yeah.
That is true.
Yeah.
Why are the fresher basalts better sequestrator? Because fresher basalts, I mean, in a weathered basalt, of course, there are already, some mineralization has happened. You are not getting exactly all the minerals where nice reactions actually take place. So that's why you already have clay minerals in case of a weathered basalt, right? So that essentially decreases the reaction rate. At least that's what the idea is.
Jyotirmoy, a small query. In places like Deccan Basalt, where there are trapped basalt continuously, so there are also zones like the colonnade zone, both in the upper and lower part of the basaltic horizons. So I think those are the zones which might it be used for both your trapping it, as well as there is a risk of you can say the release of CO2 in future as well. They could be useful as well. I think they could be problematic as well.
I agree with you. I completely agree with you. For example, the dikes as well, these cooling joints, they could also be potential leak paths.
Right.
It's true that dikes with high fracture density offer potential.
The question is long-term storage.
It's too early to answer, Avinash. We don't know. We have just started working on them. We are not in a position to form any strategy about them. We are very early with the research. Will the sequestration be probable in the thrust zones? I can't answer that. I have not studied the basalts of Arunachal Himalayas. It needs to be looked at with rigorous studies actually. Generally, but having said that, generally the faults and fractures are avoided because of potential leak. At least if the faults actually reach all the way up to the surface, then you potentially avoid such areas.
I think
there could be multiple pathways.
Yeah, zones of Garhwal
the
Himalayas.
CO2
Same
can link.
answer. I have not studied them.
Same. I think
In I
same
have
thing
not
will
studied
happen.
them about CCS potential. However, if it is extremely fractured, I mean Himalaya is faulted. Some of the faults, of course, reach all the way up to the surface, and my guess will be perhaps no. But having said that, I have not studied them.
But one day after you start this work in the field, I think it would be very good to show us how you really do the things. How do you insert the carbon dioxide into the basalt? If you can tell this to the community, and that would be really exciting.
Yeah, sure.
Or if you have some sort of videos or something like that, if you could, I was expecting this thing in fact today, that you will show something like that, so that in fact you can see that it has triggered a lot of queries among young people. So you can imagine how it would be if you can show this thing. I am sure that a lot of people will be interested in undergoing research or carry out some new work on these aspects.
Yeah, so I think that is more to do with a course. I mean, nowadays people are also considering, for example, Colorado School of Mines right now offers a course on carbon capture and storage. So we are also in IISER Bhopal if we have time to.
Avinash has another query.
Yeah. You have generated traction network. The preliminary porosity is quite. It's not the porosity; it's the permeability which is promising. Porosity still remains within 2 to 5%, 10%, not more than that. It's the permeability which is very promising. Fractures are excellent permeable pathways, but the fracture porosity is generally not that high. Sir,
if you start with fractured rocks, then isn't it more likely that the fractured rocks should be altered by the geological processes before you do sequester your carbon dioxide?
Sir, what we have seen in the field, no, sir. Sir, at least what we see in the field, the dikes are much more fresher than the country rocks.
That are very shallow, no? That are very shallow level things.
No, even at the deep, the fractures.
But the fractures are pathways for the water circulation, so that
is true, sir.
More likely that it would alter the host rock.
Theoretically, I agree with you, sir, but the field observation do not actually confirm that fact, that the fractured basalts are not more weathered as far as, whatever basalt I have seen, we have not, it's not that we could categorize that the fractured basalts are more weathered. That is not something what I have seen. There are plenty of exposures where things are completely weathered. They could be fractured in before, I don't know, because through the fractured planes, there is also this exfoliation weathering going on. However, there are plenty of fractured basalt present which are completely fresh.
People have done this type of work in the other part of the globe. Sequestration in basalt.
No, the work just has started maybe 1 or 2 years before. There are not many papers, not many work.
Okay, we'll have to, so it will all depend how it really works for next couple of years.
Yeah.
And then only we'll be having some idea whether basalt is a suitable area for carbon sequestration.
No, there is a lot of work, and there are a lot of projects which are currently being granted as well. So hopefully we will be able to get some meaningful understanding of Deccan from CCS perspective. There are too many unknowns right now.
So the permeability is a very important thing, So I'm not really sure at depth how this the porosity will be connected. Because
permeability you can calculate with. If you use standard fracture compressibility equations.
Theoretically you can calculate. Theoretically, really you can calculate. But theoretically you can calculate. That's true. But how it is connected, it depends in a natural system.
The fractures are generally connected. The porosities, the vesicles are sometimes not that connected.
That's what
fractures
I'm saying.
Are generally connected because they are cooling joints and they are like more extensive. They are not small scale, so they intersect one another and they are generally connected.
These cooling joints are really up to 4 kilometers, not below that.
No,
this cooling joint.
This is like
4 kilometers. Yeah.
No, they are everywhere. Because the Deccan, one layer after another was exposed to the surface, right? So one layer came that was exposed to the surface, then another layer came. So it's all basalt. It's not gabbro. It's not plutonic rock. So being basalt, although they are now subsurface, they have a lot of cooling joints.
Okay, I got your point.
Hello, Jyotirmoy.
Yeah. Yes, sir. Hello, sir.
Thank you for the very comprehensive talk. I have some query.
Yes, sir.
I see from the literature that there are major natural fracture zones and the rift zones in basalts. Will they be useful?
Well, there are two things to see to it, sir. They will be high permeability pathways.
Yeah.
One thing, they can be good for getting permeability in your formation. However, they also pose a associated risk of leakage.
So in that
also
case,
groundwater contamination.
Yeah. In that case, do you have to be away from these kind of fracture zones?
Difficult to say right now, sir. In one way, they will be very good because they have very high permeability.
Okay.
However, in the other way, they could be potential contaminant to your groundwater as well as potential pathways for leakage. So they being integral part of the Deccan Basalt. You cannot avoid them. How to deal with them, we don't know yet.
I see. But you want to choose a potential site.
Yeah, absolutely. Yeah.
You have to consider all these things now.
Absolutely. There is no doubt about that. And that's why we are looking at different aspects of it.
Any more queries from my young students and research scholars? Please, if you have any query, please ask Dr. Jyotirmoy. Is there to excite you more?
No, but I encourage, if you are interested in this topic, there is a lot of opportunity right now, and I think structural geologists have a good role to play. If you want to form a project, I think I can help you as well. So yeah.
Okay. So it's a good gesture from Dr. Jyotirmoy that is going to help you out in framing some projects on similar topic.
Yeah, this is right now is a focus. So, but there is a good chance that you will get a good project if you can form it well.
Okay, Jyotirmoy, it's a fantastic talk, and we really enjoyed it. And if there is no more queries, I think we are going to give you a good round of applause. Sandip, are you there?
Yes, sir.
Then you can conclude. You can conclude the session if you don't have any more queries from the panel.
Right, sir.
But before that, I will ask those DMs are already left. Yeah, I think he has left. So, okay, you can conclude the session.
Okay, so thank you everyone for being with us during this online e-lecture, specifically on a Sunday and Sunday afternoon. So thank you all for joining us. And there where I have in the screen a few minutes back, there were I think more than 40 participants. So unlike last, I think a couple of lectures, this lecture attracted more members in our community. So thank you all for being here, and I thank Jyotirmoy as well for taking this opportunity to welcome more projects on carbon sequestration, be it in Deccan Basalt, be it somewhere else. So definitely it will open several new questions and obviously new opportunities as well, what I feel from the discussion we had. Okay, so thank you everyone. And we'll be again meeting you soon for the next monthly lecture in late April. Thank you.
Thank you. Thank you.
Bye, everybody.
Bye.
Thank you, Jyotirmoy.
Thank you.